Now let's look at one simple algorithm to compute 3D convex hull. So this is the gift wrapping algorithm. So I will not spend too much time on it because it's very simple and quite inefficient algorithm, but when the size of the convex hull is small, this algorithm could actually be competitive with the best algorithms. The idea is very similar to 2D. In 2D we'll wrap a line, in 3D we'll wrap a plane around the convex hull. The first thing we do is we project the convex hull into 2D. So we project the points into 2D and we create the 2D convex hull of this set of points. So lucky for us, it is easy to envision the 2D projection of this point set. In particular, it will simply be this outline picture that exists here. So this will be simply the projection of this convex hull into 2D. Now we take one edge of this 2D convex hull as a starting point. In particular, let's take that edge. Imagine a vertical plane, a plane that is vertical, that is perpendicular to this line, the line that goes through this edge, and it's perpendicular to this the plane that we see this picture on. So it goes infinity to the top and the bottom. Clearly this plane will only touch the convex hull on this edge only. It will not have any other contact with the convex hull. So the next thing we do is that we will slightly rotate, or in other words, we will slightly turn this plane around this edge until it touches the next point of the convex hull. So if I look at this, if I look from the side, what I see here is that I will see this edge as one point, and I will see the plane as a vertical line, and then I will tilt this very similar to the 2D convex hull around this edge until it hits another point of the convex hull. So by going through all of the input points, I could basically compute the angle between that plane and the vertical plane and the plane given by that rotation. So I will get the smallest angle of rotation, and that will give me the first face of the convex hull. As opposed to 2D, now I have two choices for extra rotations. I could try to discover the adjacent face of this edge or this edge. I pick one of them. For example, I pick that one, then I discover the next face of the convex hull. And again, I have two choices. For example, I pick this one and I keep on doing this. At some point, I will get a point that if I do one more fold, I might get back to where I started. So this algorithm, if it's implemented naively, could run in an infinite loop where I just keep on wrapping. However, using a simple idea, we could avoid this infinite loop. And the basic idea is just simply use a DFS, a graph, a depth first search, and a graph that is defined by the faces of this convex hull. And the basic idea is that you mark every face that you discover is marked. So therefore, when I realize that the adjacent face of this triangle is now a marked face, then I will no longer fold my plane on top of that. So I will fold the other way. And once all the adjacent faces of all the faces have been discovered, I have found my 3D convex hull. This algorithm is quite inefficient. In particular, for every folding that I do, I'll need to spend linear time because I need to go through all the points, all the input points. And if size of the convex hull is h, this will take O of n times h time.